The GE9X is the largest and most powerful passenger jet engine ever built. It's so wide across the front that you could almost fit the entire body of a smaller plane inside it. It hangs under the wing of the Boeing 777X, the newest giant twin-engine jet in the world, and together they're an incredible piece of engineering. This documentary explains how this monster engine works, part by part, from the moment it wakes up to everything it powers while it flies. First, the bones of the engine. Deep inside, there are two separate spinning shafts, one tucked inside the other, and they spin at different speeds. The faster inner one is called the high-pressure shaft, or N2. The slower outer one is called the low-pressure shaft, or N1. Now, an engine squeezes air using rows of blades called compressor stages, and it pulls power back out using rows of blades called turbine stages. On the GE9X, the fast N2 shaft carries an 11-stage high-pressure compressor and a 2-stage high-pressure turbine. That 11-stage compressor is a big deal because it squeezes air harder than any other engine of its kind in the world. The slower N1 shaft carries a 3-stage booster, which is a smaller low-pressure compressor plus a 6-stage low-pressure turbine at the back. And right at the front, ahead of everything, sits the star of the show, the enormous fan, about 134 inches across, the biggest ever put on a jet engine. Here's a cool detail about that fan. It has only 16 blades, and they're made of carbon fiber, a material that's super strong but very light. Older engines needed more blades, but thanks to modern materials, GE could use fewer, thinner blades. Fewer blades means smoother airflow, less weight, and a quieter, more efficient fan. So even before it starts, this engine is built to do more with less. Now, how does an engine this huge actually start? You can't just flip one switch and roar to life. It happens through a careful chain of steps, and each one sets up the next. It all begins with the plane's battery. The battery only holds a little bit of power, but it's just enough to wake up a small helper engine tucked in the tail of the plane called the APU. Once the APU spins up, it becomes a powerhouse of helpers. Its generator floods the whole plane with electricity, and that electricity powers the engine's brain, a computer called the EEC that sits right on the engine. This brain will run the entire startup on its own. The APU provides one more thing the engine needs to start pneumatic power, which is just high-pressure air. There's also fuel to line up. For starting, the plane draws fuel from one wing tank, where pumps push it out toward the engine and hold it ready at a valve. With power flowing, air ready, and fuel waiting, the engine can begin its start. Here's how the start actually unfolds. The brain opens a valve, and that high-pressure air from the APU rushes in and hits a part called the air starter. Think of the air starter like a strong gust of wind spinning a pinwheel. This starter drives a gearbox, which is basically a hub of spinning connections. Through a clever set of shafts, the gearbox reaches in and begins turning the N2 shaft. As N2 starts to spin, air begins flowing through the core of the engine, and this triggers a neat chain reaction. That moving air pushes on the turbine blades near the back, which nudges the N1 shaft into motion too. Once N1 turns, the giant fan up front starts spinning, and huge amounts of air begin flowing around the engine. At this point, the engine is breathing, but it isn't burning any fuel yet. It's just spinning on borrowed air from the APU, and then comes the moment of fire, but the brain is careful about timing. It waits for N2 to reach a certain speed before it lets fuel in. And the fuel takes a surprisingly long journey before it ever burns. So let's follow the path it travels. First, the fuel reaches the main fuel pump, spun by that same gearbox. The pump cranks up the fuel's pressure and pushes it onward. But before the fuel can burn, it makes a smart pit stop. It flows through a heat exchanger where the cold fuel actually cools down the engine's hot oil, and the fuel warms up a little in return. Two useful jobs at once. From there, the fuel passes through a filter that strains out any tiny bits of dirt, keeping everything clean. Then the fuel arrives at the most important control point, a unit that carefully decides exactly how much fuel the engine gets. Any extra it doesn't need gets looped back around. This unit waits for the brain's command before it lets fuel through to burn. When N2 finally reaches the right speed, the brain sets up the fire. First, it switches on the ignition, which works like a spark plug, creating a powerful electric spark inside the engine. It uses one igniter and keeps a second one as a backup, just in case. A few seconds after that spark is ready, the brain opens the fuel gate at last. The fuel passes one more sensor that measures exactly how much is flowing, which helps the crew keep an eye on the engine's health. Then it enters the combustion chamber, the burning heart of the engine, through 3D printed fuel nozzles. Yes, 3D printed, meaning these parts are built up layer by layer by a machine, which lets GE create shapes far too complex to make any other way. These nozzles spray the fuel into special swirling slots that gently slow the incoming air and mix it perfectly with the fuel, giving it time to burn cleanly and completely. And then it lights. The fuel and air ignite and hot gas blasts backward onto the turbine blades. Since those turbines share shafts with the compressors, spinning turbines mean faster spinning compressors, which shove in even more air, which makes even more power. It's a self-feeding cycle that keeps building strength. The whole engine spins faster and faster, and thrust steadily climbs. Once the fire is hot enough to keep burning on its own, the brain shuts off the spark since it's no longer needed. A little later, it closes the air valve and cuts off the APU's starter air, disconnecting the starter now that the engine can run by itself. Finally, the engine settles into a smooth, steady idle. The brain signals that the start is complete, and everything resets, ready for next time. The engine is now alive and running entirely on its own. But running at idle is just the beginning. Pilots control the engine's power using the thrust lever. When they push it forward, the lever signals the brain, which tells the fuel control unit to feed in more fuel, and the engine's thrust rises to match. Pull it back and the engine eases off. Smooth and simple. Now here's something most people don't realize. Pushing the plane forward isn't the only thing this engine does. A running jet engine is also a giant power plant, and it delivers 3 important kinds of power to the aircraft. Let's look at each one. The first is electricity. The plane runs on electrical power for nearly everything, from its computers to the cabin lights to the passenger screens. As a safety rule, the plane always wants at least 2 sources of power running at once. If it ever drops to just one, a smart system starts shutting off the non-essential stuff first, like galley ovens and entertainment, to protect the important systems. With the engine running, a generator on its gearbox makes electricity. But there's a tricky problem to solve. The plane's electrical parts need a steady, exact rhythm of power, a frequency of 415 Hz. The trouble is, the engine's speed constantly changes as pilots adjust thrust, and a changing engine speed would make a messy, changing frequency that could fry the plane's electronics. So, GE uses a clever device that works like a gearbox for speed. No matter how fast or slow the engine spins, this device keeps the generator turning at one constant speed, so it always pumps out a perfect steady 415 Hz. And the GE9X has a bonus safety trick. On most planes, if that main generator overheats and has to shut down, the engine loses all its electrical power. But the GE9X carries a backup generator. It doesn't have that fancy constant speed device, so its frequency is uneven. To fix that, its power runs through a converter that smooths it into a steady 415 Hz and feeds just the most essential systems. So even in a bad situation, the engine can still keep the critical stuff alive. The second kind of power is hydraulic power. Hydraulics use pressurized fluid to move heavy things, like the flaps on the wings and the controls that steer the plane. The engine drives a pump that squeezes hydraulic fluid up to 3,000 pounds per square inch, a very high pressure, and pushes it out to move control surfaces all across the aircraft. It runs automatically whenever the engine is turning. The third kind of power is pneumatic power, which is simply hot, high-pressure air pulled from inside the engine. This is called bleed air, because the plane bleeds a little air off the compressor to use elsewhere. A computer manages this carefully. It first closes the APU's air valve, since the APU was only needed for starting and isn't required anymore. Then it opens valves to draw air from a middle stage of the compressor. Here's a clever balancing act, though. Sometimes that air isn't strong enough, so the computer pulls from a higher, more powerful compressor stage instead. The catch is that higher stage air is dangerously hot and could damage the plane's ducts. So the computer opens another valve that grabs cool air from the engine's big fan and runs the hot bleed air through a cooler, an air-to-air heat exchanger that brings the temperature down to safe levels before it flows through the plane. This bleed air does a ton of jobs. It feeds the air conditioning, helps start the engine on the other wing, warms the cargo holds, and keeps ice off the wings. Speaking of ice, the engine also protects itself. In freezing weather, ice can build up on the front lip of the engine, which is extremely dangerous. So a detector senses the icing and tells a controller to send warm compressor air swirling around that front lip, melting the ice away. When the bad weather passes, it shuts the system off. This ice protection is built right into the engine, keeping it safe in the worst conditions. Now, here's a piece of honest history that shows how hard this engine was to build. During its testing back in 2019, engineers found a real problem. In one part of the compressor, the air was running hotter than it should, and it was wearing out some small guide vanes too quickly. Left alone, those parts would have failed early. So the engineers went back, redesigned the little arms that control those vanes, and retested everything until it was right. That fix is a big reason the 777X was delayed, but it's also proof of how carefully these engines must be perfected before they can ever carry passengers. And that careful work paid off, because the GE9X is packed with cutting-edge tricks the older engines never had. Its burning heart uses a special new design that mixes fuel and air to burn cleaner, making far less pollution. Even more impressive, dozens of its hottest parts are made from a material called ceramic matrix composite. It's lightweight yet can survive brutal heat that would weaken normal metal, and it needs far less cooling air, which saves even more energy. All of this together is why the GE9X burns about 10% less fuel than the mighty engine before it, while also being the quietest engine GE has ever built. So there it is. It starts with 2 spinning shafts and a giant fan. A careful chain of steps brings it to life. A single drop of fuel takes a long journey to the fire, and the engine roars into a steady run. But it does far more than push a plane forward. It's an electricity maker, a muscle-moving hydraulic pump, and a hot air supplier, all bundled into one machine. The GE9X is a marvel with over 35,000 parts working in perfect harmony, and every single time a 777X climbs into the sky, this incredible engine is the reason it flies.